Students, good morning. Today we'll continue the quantum chemistry. Under that we'll discuss about wave function and its interpretation. Okay, so the wave function, which is represented by psi, and as you know, the electron is having wave character, and psi is the amplitude of that wave, that electron wave, and which describes the distance and the direction of the wave with respect to the nucleus. Okay, there are two interpretations. Say one is given by Schrodinger and the another one is given by Bohr and Heisenberg. Say under the first interpretation, which is given by Schrodinger, he explained in terms of charge density. He explained in terms of charge density. If psi is the amplitude, if psi is the amplitude of the de Broglie's matter wave at any point in space, then the particle density is directly proportional to square of the wave function. It is directly proportional to square of the psi function, and or we can say hence the square of the psi, that means amplitude of the electron wave, is a measure of particle density. If we multiply the particle density by the charge, then it gives, say, the charge density. But this interpretation holds good when the wave mechanics was applied to stable states of Bohr or a Bohr's theory. When it is applied, it is applicable, or it holds good when it is applied to the, say, stable states. That means the wave is a standing, or it is a stationary stable state. Okay, but it fails when the material particle becomes wave, or it fails when the waves interfere or collides with each other. Okay, so this is about the first interpretation that is given by Schrodinger, and the second interpretation is which is given by Bohr and Heisenberg's. So according to here, say that means psi has no physical say meaning, actual physical meaning, and psi square is not a measure of, it is not a measure of, see, the particle density or a charge density at any point, but it is related to, probability of finding the electron, say, probability of finding the electron in the vicinity of the, say, nucleus, and that is at any given moment. Okay, so the psi, that is the probability of the psi, it is denoted by p, and which is equal to psi square. Okay, and say where the probability p is nothing but it is the probability of finding the electron at the point, say, xyz, and that is given by pi p is equal to psi square, or it is nothing but psi at xyz and psi star at xyz. So here the psi star is the complex conjugate of psi. Complex conjugate of psi. That means, say, uh, if the psi is an imaginary, if it has imaginary values, then when it is multiplied by conjugate, it gives the real values, because the probability of finding the electron at any point, either it may be a large or it may be a small or it may be zero, but it never be imaginary. So hence, to convert, that means imaginary values into a real values, say it is multiplied by its conjugate. Okay, so the probability of, say, probability of finding the electron never be imaginary. It cannot be imaginary. If psi is real, then psi is equal to psi star. If psi is real, then psi is equal to psi star, and therefore p is equal to psi square. P is equal to psi square. Is it? Thus, psi must be a single valued, and at each point or each and every point, it must be a single valued at each and every point, and it must be finite. It must be finite, and its absolute values at all the points. its absolute values at all the points. So must be such that integration of psi into psi star into d tau is equal to 1, where the tau is the general symbol for all the coordinates, okay. So eigenvalues and eigenfunctions, okay. So you are well familiar with Schrodinger wave equation, which is derived with respect to, say, the electron wave, isn't it? And the electron should obey this equation. Say when you solve this equation by putting the psi value, and you can calculate or you can get the value for total energy, that is capital E, is it? So now say by putting the different values of psi, isn't it? So you will get different values for E. See, there are several values of E. So we can get several values of E, that is total energy, capital E, for different psi values. Okay. So now the values which are acceptable values, which are acceptable, okay, E, and they are said to be eigen values, and the corresponding psi, they are said to be eigen functions. So okay, eigen functions. So as you know, the psi can be defined by taking, say, xyz coordinate values, and by putting these values in this, say, if we get the acceptable, there are several solutions, okay, there are several points. Just you if imagine, say, there are many points around the, say, nucleus, okay, and at a particular point, okay, at a particular point of psi, say if it gives the acceptable value of E, that is eigen value or the energy, total energy of the electron, and that acceptable value of energy is said to be a eigen value, and the corresponding psi for which we got that value, it is said to be a eigen function, okay. And in order to have the acceptable energy, that is the total energy of the electron, and the psi must, say, there are certain conditions for the value of psi. Say the first one is the psi must have finite values. That means it must be in the vicinity of the nucleus. Second one, psi must be a single valued. So at a point, the value of psi must be a single. And psi and its derivatives must be continuous with respect to its variables. Say psi or its derivatives must be continuous with their variables, x, y, z variables, isn't it? So if it obeys, if it agrees these conditions, then see the resulting value is said to be a eigenvalue, and the corresponding psi value is said to be a eigenfunction. Therefore, for every eigenfunction, there is one eigenvalue if it obeys these things. Okay. So with this, we'll discuss about the next one, orthogonality and normalization. Okay. Thank you.